Yeah, so hello everyone. My name is Andrei. Yeah, I was asked to talk about cold atoms today, but to be honest, I'm a big supporter of room temperature atomic ensembles and warm atoms. So we won't talk specifically about cold atoms, but atoms in general. Yeah, so a few words about myself. Yeah, I did my bachelor's in Moscow at Moscow Institute of Physics and Technology. So I've graduated from aerospace department, but during my second year, I learned about new and exciting field of quantum technology. And like back in the day, like I guess like 2012, that was a moment when the quantum hype was gaining momentum. Yeah, so it was very interesting and exciting. So I actually started learning it on my own pace. And yeah, at some point I was ahead of the curriculum by like several months. Yeah, and like, yeah, I consider myself, at least to some extent, self-taught quantum physicist. Yeah, so yeah, after I graduated, I wanted to apply my theoretical knowledge in practice. And I chose ultra-cold quantum gases lab at the University of Alberta, run by Lindsay LeBlanc. So at the moment, it was a newly established lab. So me and my friend, we were the two only people in the lab. And yeah, during my master's, I've built from scratch an ultra-cold apparatus for creating ultra-cold atomic ensembles. And then I did my PhD in the same lab. And yeah, during my PhD, I actually decided to move from cold atoms to warm atoms to see if we can have quantum phenomena and observe and use them in room temperature ensembles. And indeed we can, and we'll discuss it. And yeah, after my PhD, I decided to push it even further and look if we can observe or use quantum phenomena, not just in room temperature systems, but actually systems inside living things. That's why I joined Clarissa's lab here at the UCLA as a postdoc. All right, so we'll begin about a brief introduction to the field of atomic physics. Usually when I tell people that I'm doing atomic physics, this is what comes to mind. So it's either I'm working on atomic bombs or at best atomic energy, but this is not the case at all. So in fact, according to modern classification of physics, these two applications are misnomers, so they don't relate to atomic physics at all. They are rather nuclear physics applications. So yeah, if you're interested in bombs and electric energy, you need to do nuclear physics, not atomic physics. And on the left, this is what a typical atomic physics experiment looks like. So you have a glass cell with metallic vapor connected to an ultra high vacuum and usually surrounded by a bunch of optics. So yeah, if you work especially with cold atoms, like in 90% of cases, this is what you're going to be working with. So at the end of the day, it's actually optics. And actually, these two applications are not just different, they sort of on opposite ends of energy spectra. In nuclear physics, you usually work with very high, extremely high temperatures and extremely high energies, while in atomic physics, especially in cold atoms, you actually creating the coldest temperatures in the universe. So yeah, very different things. All right, so I'd like to discuss what an atom is. It might sound silly, but the problem is in different fields or subfields. Communities can use the word atom to refer to different physical systems. So I just want to make some clarifications for our presentation. So for the purpose of this presentation, when we say atom, we refer to a quantum system that consists of a positively charged nucleus. surrounded by a bunch of negatively charged electrons. And here I would like to stress out that we working only with a single nucleus. If you have more than one, then we call it a molecule. And surprisingly, the physics of molecules is quite different from physics of atoms. It's more complicated, it's more advanced. So yeah, in this presentation, we will be focusing only on atoms, so on systems with a single nucleus. The second point is this system is electrically neutral. So we already had a separate talk on ions, which is basically the same system, but when you have imbalance in electron number and proton number, so your system has a charge. In this case, actually the physics, like the internal physics of the system is the same, whether you're talking about charged ions or neutral atoms. But the tools, the techniques that you use to manipulate quantum states of the systems are different enough to have separate talks. So in this talk, we're talking about neutral atoms. And finally, we will be talking about atoms that are isolated. So they're either completely alone, so a single atom system, or they in a dilute vapor state. So we won't be talking about atoms inside liquids or inside solid states. And even though in solid states, you can have atom-like systems, and I guess Clarice already presented the talk on NV centers in diamond, which act and have similar physics to atoms, but again, different tools, different techniques to manipulate. So yeah, today we're talking about atoms in vapor state of matter. And yeah, to be more specific, we'll be focusing on atomic optics, which is studying interaction of atomic electrons with external electromagnetic fields. Now, what types of atoms are usually used in atomic physics experiment? So in many cases, labs work with alkali metals. So those are atoms from the first column of the periodic table, so right below the hydrogen atom. The thing about these elements that they have odd number of electrons, and electrons occupy quantum state in such way that you have a bunch of fully filled atomic orbitals and one single electron on the outer shell. So here is, as an example, is lithium, where you have two electrons occupying the lowest energy orbital, and 2 is the maximal number of electrons on this orbital, and only a single electron on the outer shell. As a result, what usually you make an approximation where you completely ignore those electrons. So you consider only the outer electron as being as it interacts with external electromagnetic fields. And further than that, since these electrons occupy the lowest orbitals, you say, well, like the outer electron sees the reduced electric field, basically, right? So those two lower energy electrons effectively screen out the positive charge of the nucleus. So your outer electron sees only single positive charge in the nucleus. So essentially, alkali metals are single electron atoms within this approximation. And thus, in most cases, their physics is very similar to physics of hydrogen. And hydrogen is definitely the most studied atom in physics. So you can use the insights from hydrogen physics and apply it to alkali metals. So it might seem as a kind of rough approximation because, well, for example, in the case of rubidium, which is the most widely used alkali metal in experiments, you basically disregard 36 out of 37 electrons. And yet it does make some corrections. So if you care about actual numbers, for example, frequencies of your transitions, then you need to take care of all electrons in one way or another. But if you just want to understand the system or develop an intuition and intuitive pictures, to be honest, this approximation is quite good for that. Now let's take a closer look at the atomic energy, because in quantum technology, usually when you talk about quantum states, what you're actually talking about are energy states. And in atomic physics, when you're talking about energy, usually you're talking about energy of that single electron on the outer shell. It has three types of energy, which are connected to the three main parameters of an electron. First one is a mass that is connected to the kinetic energy. So basically, it shows you how much energy you need to spend to change the electron's speed. The second fundamental property is electric charge, which shows you how strongly it interacts with the nuclear electric charge, and it's usually represented by Coulomb energy. And finally, it turns out that an electron has a magnetic dipole due to its spin, and as a result, it has a magnetic energy provided that there is a magnetic field in the system. And here I would like to stop for a moment and discuss in more detail what spin is, because sometimes I can see some misconceptions about that. So spin is an intrinsic angular momentum of a particle. Here, intrinsic means that it is not due to particle's motion, but it's like an internal parameter, same as mass or charge. And you cannot get rid of it by going to a different reference frame or something like that. So it's always there. It's represented in units of Planck's constant, which is actually true for any angular momentum in quantum mechanics. And it's quantized as any quantum angular momentum, but unlike orbital quantum angular momentum, it can have half integer values of Planck's constant. And finally, it is not actually the same as a magnetic dipole. And to be honest, very often in field of atomic physics or in quantum technology in general, spin and magnetic dipole are used interchangeably. Or I would even say, like, whenever people say spin, they actually refer to magnetic dipole, because that's what ultimately determines the energy, not the spin itself. Excuse me. So it is usually justified because there exists a straightforward connection between system spin and its magnetic dipole, but not the same thing. For example, in case of a photon has spin of 1, but it has no magnetic dipole. Or both electron and proton have spins of 1/2, but their actual magnetic dipoles are different by 3 orders of magnitude. So electron's magnetic dipole is 2000 times stronger than that of a proton. And even in case of electron, its spin and magnetic dipoles are anti-parallel. So not the same thing, but yeah, just keep in mind that usually spin and magnetic dipole are used interchangeably. All right, so the main contribution to atomic energy is known as gross energy, and basically it's a sum of the kinetic energy of the electron and its Coulomb energy. It turns out that different quantum states can have the same energy, and basically those different states correspond to different portion of how much energy is in kinetic energy and how much energy is in the potential energy. So for example, if you have a spherically symmetric state, your average kinetic energy is typically 0. And if you have a non-zero orbital angular momentum, then some portion of your energy is in your kinetic energy. So here's this expression is a Hamiltonian. So it's a quantum operator. So basically it's a matrix which tells you how to find the values of the energy. And here are the possible values of the energy. So as always in quantum mechanics, they are quantized, and the number that determines this quantization is called principal quantum number. So basically, the larger this number and is, the more energy the atom has, and we call it more excited. So in terms of transition frequencies between several gross energy levels, there is no real lower limit, because as n is when it's very big, basically the separation between two neighboring states goes to 0. So there is no lower limit, and yeah, I guess the highest energy for this transition that you have corresponds to ionization of the atom, and yes, I remember it goes like at the ultraviolet frequency. The second order of magnitude in terms of energy is what is called fine structure. So basically, it arises due to interaction of the electron's magnetic dipole with the magnetic field, with the relativistic magnetic field, which it sees when it circles around the nucleus. So you can easily understand it if you use Bohr's semi-classical model of, say, hydrogen atom. And if you go to the electron's rest frame, in this rest frame, the nucleus revolves around the electron. And since the nucleus is charged, it creates a magnetic field. And then whether electron's magnetic dipole is aligned or anti-aligned with this magnetic field, you have either lower or higher energy. So yeah, the famous transition that is identified by this fine structure is D-line in alkali metals. So this is the optical transition without changing the principal quantum number. So here you just go from the state with no orbital angular momentum to the state with 1 unit of orbital angular momentum. And then depending on the projection of electron, you have two levels that in alkali metals corresponds to optical transitions, and these two transitions are most widely used in atomic physics applications. So either for cooling of atoms or performing some quantum gates. And finally, the lowest energy contribution to atomic energy is the hyperbind structure. So basically, the nucleus has a magnetic dipole as well, and it creates a magnetic field. And then whether the electronic magnetic dipole is aligned or anti-aligned with this magnetic field, you have either increased energy or decreased energy. And this effect actually leads to splitting of the ground state. So the state that otherwise has 0 average kinetic energy, so it doesn't have any spin orbital interaction, but whether the electron spin is aligned or anti-aligned with the nuclear spin, you have different energies. So usually it's represented by the total atomic spin. So in case of rubidium-87, you have nuclear spin of 3/2. So you can have either total atomic spin of 2 or 1. So this is a magnetic dipole transition typically in microwave range. And this is very important transition since it's used for atomic clocks, and we'll talk about it later. So now I'd like to discuss some techniques that are used to manipulate atomic states. First one is laser cooling, or also known as Doppler cooling. here the purpose is to reduce energy of atoms. So yeah, first of all, I need to clarify that whether when we say cold atoms, what we mean is not the temperature of each individual atom. So it's either an temperature of an atomic ensemble, or alternatively, you can be talking about kinetic energy of a single atom represented in terms of or in units of temperature. So basically, when we cool atoms, what we do is we essentially slow them down. So we slow down each individual atoms. It can be done with laser lights in these configurations. So basically, you have in 1D, you have two counter-propagating laser beams. And if you choose a frequency of laser to be below, let's say your D line, so below an optical transition, then whenever atom is moving towards, like in opposite direction to a photon, in the reference frame of the atom, the frequency of the ongoing photon is increased due to Doppler effect. And Doppler effect is actually a classical effect, so it's true in classical physics as well. So whenever you're moving towards a frequency source, you experience emitted wave at a higher frequency than at the reference frame of the source. So when an atom moves towards the light, it experiences light at a higher frequency. So this frequency is closer to the transition. So it is more frequently absorbed. Sorry, give me a second. Someone is knocking on my door.
This is a good time to ask for questions.
Oh, hi. How are you? Did you get the notice from Susan?
Are there questions in the chat? Or feel free to unmute yourself and say. Cool. We're talking about Doppler cooling. We're talking about the Doppler effect. So the Doppler effect is the reason why, say, a siren changes. Apparently, it's well. Go for it, Andrei. I was going to. You're muted. I muted you. Sorry.
Yeah, I'm really sorry. So apparently my landlords decided to show my place to other people and they did not give me a notice. So
Good.
Sorry. Okay, yeah, so in a nutshell, basically the principle of cooling is you, by carefully choosing the frequency of your laser light, you make atoms want to absorb the light that travels in the opposite direction. So the atom gains momentum kick in opposite direction and it slows down and the whole atomic ensemble cools down. The second application is magneto-optical trapping. So whenever you have the same arrangement, so you have three counter-propagating laser beams, then you apply a magnetic field that has very sharp gradient and it has zero at the intersection of the laser beams. Again, by carefully choosing the direction of the polarization of the magnetic field and polarization of laser beams, you can make the atoms to want to absorb photons that move towards the trap center. So as a result, atoms get more momentum kicks pointing toward the center, which creates a restorative force leading to trapping of the atomic ensemble at the intersection. This is called magneto-optical trap, and usually this is the first step in many cold atom applications. And this is what it looks like in real life in our lab. So you can observe it with the naked eye due to fluorescence that atoms re-emit in this process. And basically, it looks like a glowing dot in the middle of nowhere because the atoms are inside a vacuum chamber. Another very important application is called optical pumping. So here, excuse me. So here you just apply a light which is resonant with one of the transitions, one of the ground state transition, and as a result, it excites atoms to an excited state from where they can decay to either the original state, in this case they will absorb light again, or they can decay into the other ground state. Here, because the frequency separation between these two states is in microwave range, atoms do not interact with the optical light anymore because it's very far detuned. And essentially all your atomic ensemble ends up in a single state. So for example, state where all electronic spins are anti-aligned with the nuclear spins. And a modification of this technique, if you use a light which is circularly polarized, you not just orient all electron spins in the same way with respect to nuclear spin, you also orient them in the same way with respect to basically laser beams axis. So you can make all electronic spins pointing in the same direction along or anti-parallel to the laser axis. And as a result, all your atomic ensembles becomes magnetized. Because here all spins point in random directions, so net magnetization is 0. In this case, all spins point in the same direction, so yeah, whole ensemble is magnetized, and it can be used for either magnetic trapping, so trapping in a magnetic field, or for measuring external magnetic fields. And we discuss all these aspects later. Yeah, so here's a example of magnetic trapping. Yeah, so you do your optical pumping, you orient your spins in single direction, it becomes magnetic, then you apply magnetic field which has a 0 somewhere, and in this region the energy is minimized, so all your magnetized atoms are confined in this region. So usual magnetic traps are used as an intermediate step in cooling. So magnetic traps are convenient because by varying magnetic field you can move your trapped ensemble, and then there are techniques where you can get rid of the fastest atoms in this ensemble to cool the ensemble down. And the final application that I would like to discuss is called optical dipole trap. So basically here you have an optical beam which is far off resonance with any atomic transition, so it's not being absorbed. And it has a focal point somewhere in the region of atoms. And in this focal point, it has very sharp electric field gradient. So even though the light is not absorbed, it still interacts with the atom, so it still affects its energy. And so whenever you apply an electric field, you actually polarize an atom, so you create an even charge distribution. And if you have an electric field gradient, which is again the case at the focal point, then your negative charge experiences a different force from your positive charge. So you have a non-zero net force, which is what creates a trap. Excuse me. And this is widely used nowadays in quantum computer, where you trap individual atoms in these focal points, and then you can even move them around, or as an intermediate step to achieve the coldest possible temperature in atoms. So again, in this kind of trap, you can get rid of the fastest atoms to lower the temperature of your ensemble. And this is what was used to achieve Bose-Einstein condensate, so the coldest matter in the universe. And here's a picture of my previous lab, where there's a trap called atomic ensemble into optical dipole traps that intersect each other.
I'm sorry, can I ask you a quick question? Yeah.
Yes.
So I'm just curious about some fundamental setup. So how did you sort of like purify the sample because from your previous photo, I think it looks like like a vapor. I'm not sure what. How did you only select the atoms that you want? For instance, the rubidium. How is that done? Thanks.
Yeah. So basically, it comes down to the design of the whole system. So originally, just let me go back here. Yeah, so you have a vapor cell which is connected to an ultra high vacuum system. So you basically pump out everything from it. So you have vacuum there. And then basically you either use like a metallic droplet of rubidium or a metallic strip, and you heat it up and you release only rubidium vapor. So by design, you only have rubidium inside. But the problem is, in general, you have two isotopes of rubidium, rubidium-85 and rubidium-87. And if you want, well, usually you want only one of them, but it turns out that all these techniques, they are isotope specific. So you use transitions that are specific to rubidium-87. So you do cooling and magneto-optical trapping only of rubidium-87, and rubidium-85 just basically flies away.
Oh,
yeah,
so
all those techniques.
You'll be able to basically localize the isotope that you want to control.
Exactly. Yeah. So in this sense, magneto-optical trap can be considered as like isotope purification technique. Yeah.
Oh, that's very cool. Thanks.
You're welcome. Okay, so now let's finally talk about some applications. I'd like to begin with the atomic clock, which is the applications that we all use, whether we realize it or not. In fact, all our smart devices, our smartphones, our laptops and computers are often synchronized to an atomic clock somewhere. Sorry. For example, there is an atomic clock at NIST, National Institute of Standards and Technology, and they basically once in a while send out a radio signal with information about the atomic clock, which other devices use to calibrate and sync to the atomic clock. So that's why your smartphone is probably never ahead or behind the time. But now what is a clock? So a clock is a device that measures or keeps track of time or measures duration of a physical process. Now, when you think about like measurement is usually a process of comparison something to something. So for example, when you try to measure length, for example, you want to measure the length of your laptop, what you do is you put it next to a ruler or a meter stick, and you know the length of the ruler. So basically you figure out the length of your laptop by comparing it to your meter stick, which acts as a length standard. And when you want to measure time, you basically compare time of a physical process to another process with known time characteristics. So for example, a process that has oscillatory behavior. So let's say you want to know how long it takes for your laptop to run a code you wrote. What you do as you start your code, you observe some oscillatory process, for example, swinging of a pendulum, and you count how many swings it takes for your process to finish. Then, for example, if you observed 10 swings during the running of your code, and you know that one swing takes 1 second, basically you say, well, in this case, my code took me 10 seconds. So basically what I wanted to show with this example is that a clock is actually a frequency standard. So it's a system that has frequency. It should be stable, so it should take for each oscillation exactly the same time. And it's good when you know this frequency. So it might be useful to know that your code takes 10 pendulum swings, but it's much more useful if you know that it takes 10 seconds. So yeah, your clock should have stable frequency and its frequency should be known. And atoms actually solve both these problems. So as we discussed before, they have several transitions, and you know those transitions because they depend only on fundamental constants. So they depend on electrons mass, electrons charge, speed of light, and Planck's constant, and that's it. Usually those frequencies are very stable, so they don't change in time. So atomic transition frequencies don't change in time. And more than that, they are the same for all atoms of the same isotope. So whether you're working with rubidium-87 in California or Japan or Iran or South Africa, the corresponding frequency, like all transition frequencies, would be the same regardless of where you're located. So that's why atomic clock is what is used nowadays as a frequency standard. Excuse me. Yeah, and here is a brief schematics of an a bit obsolete atomic clock, but still it's very representative. So it turns out that atoms are not really the frequency sources in this setup, but rather a means to measure and stabilize the frequency. So the actual frequency source is a crystal oscillator. So for example, quartz crystal. The way it works is you apply voltage and it leads to oscillations in a perpendicular plane. And those oscillations also lead to an electromagnetic field. Then what you do is you multiply this electromagnetic field, to bring its frequency close to frequency of an atomic transition. And usually you choose the transition in the ground state of an alkali vapor. And then in this setup, usually you have your vapor cell inside a microwave resonator to basically magnify, to amplify your oscillating microwave magnetic field. And you also shine resonant light on it. So this is shown on this diagram here. So the principle is, if you don't have any microwave field, you just have the optical field. As we discussed before, it will produce optical pumping. So it will put all your atoms in a single state. And this state does not interact with the light, so your optical signal is maximized. So you have increased transmission. But when you apply a microwave field, it transfers some of the atoms from the dark state to the original state. So some light is being absorbed. So you have decrease in the optical signal. And the minimal optical signal corresponds to the case when your microwave frequency is exactly on resonance. So what you do is you take this optical signal, you convert it to voltage with a photodetector, and then you use this voltage as a correction signal that is applied back to the crystal. So this signal is used to basically stabilize your crystal at a frequency which corresponds to the frequency of your microwave transition in your atom. So in this case, you solve those two problems. Your clock is stable because you use an active feedback loop to stabilize it. And it's known because the frequency of your atomic transition is known. And in fact, you can even postulate it. And right now, the frequency standard is derived from this transition in cesium. So yeah, this is more practical application with warm temperature atoms, but nowadays, if you want more precision and more stability, you can use optical atomic clock, and those usually require cold atoms. But if you want it to be portable and easy to use, usually you would use a microwave-based frequency source, which you can in warm atoms. Yeah. Another application is a single transduction, and it uses very similar setup. And this is what I did, one of the experiments that I did in my PhD. So again, you have a room temperature vapor cell inside the microwave cavity. You use the same setup, so you send the laser light through it, you apply microwave field. And yeah, as it was discussed, if you scan microwave frequency, you'll see a decrease in the optical signal. But what we do is we actually modulate the microwave frequency with an audio signal. And as a result, like this modulation in microwave frequency is converted to the modulation of the optical signal. So what we did, we actually converted the audio signal that was encoded as a frequency modulation of the microwave field to modulation of optical intensity. So this is a classical signal transduction, and it can be done if you want to receive a microwave signal or a radio signal, then convert it to an optical signal and send it inside an optical fiber, like somewhere in the basement or a remote location. But ultimately, the community is interested in quantum signal transduction, where you convert a quantum, when you convert quantum state of a microwave photon to a quantum state of an optical photon. And this is what my previous lab is pursuing at the moment. Another applications that you probably heard of is quantum computing. So atoms are good systems for qubits because they have so many possible transitions. So for example, you have an optical transition from a ground state to a higher energy state. You have several available microwave transitions. So for example, if you take two states from excited states, you can have microwave transition due to electric microwave field, or in the ground state, you have a microwave transitions due to magnetic microwave field. So lots of possibilities. Usually, like right now, I guess the most popular platform is Rydberg atoms. So Rydberg here refers not to a specific species of atoms, but rather to a state of an atom. So a hydrogen atom can be a Rydberg atom, or a rubidium atom can be a Rydberg atom. So Rydberg means that it's very excited. So its energy is close to ionization energy. And in this state, the electron has very large orbital radius. So it interacts rather weakly with the nucleus. So it's much more susceptible to external electric fields. So it's more easier to perform some quantum gates with electric fields. So I would refer you to this nice review, which is quite recent. Yeah, so with Rydberg atoms, you can have both analog quantum simulator, which is basically like an analog computer, or you can have your gate-based computer, which is more like digital quantum computer. And atoms are particularly nice because, again, each single atom represents a qubit, and you can trap those atoms in optical dipole traps, and you can move them around. So basically, yeah, with atoms, you can have a computer whose physical position of qubits is not restricted to your chip, and you can even move it dynamically during your computation. But yeah, I'm not an expert in this field, and if you have interested in this, yeah, I really recommend to check out this project. Another related application is quantum memory, or to be more precise, photon or optical quantum memory. So here you want to store photon for some time and then retrieve it at another moment of time. And the way it can be done in alkali vapors is that you apply a very strong control field as the photon that you want to store arrives at your ensemble. So as a result, you undergo a two-photon transition, which converts your input photon into what is called spin wave excitation. So it's superposition of the two ground states. And the parameters of this superposition depend on the quantum state of your photon. So like the relative amplitudes and phases of these two states depend on the quantum state of the photon. This process is coherent and reversible. So if after some time you apply the same control field, it will convert this spin wave excitation back into your original photon. So yeah, basically you use this control field to write the input photon, wait for some time, then you apply it again, you get your same photon out. So this is storing or memory of photons. Another application that now gains more and more popularity is magnetic sensing. And yeah, I guess Clarice also discussed in her talk how in-V sensors can be used to sense magnetic fields with good precision. And it can be done in atomic vapors as well. So there are several approaches. I guess the most popular one is where you apply an optical pumping pulse to magnetize your atomic ensemble in one direction, which what we discussed before. And then this magnetization, if you have external magnetic field, this magnetization starts precessing around the component of the field which is perpendicular to the original magnetization. The frequency of this precision depends on the corresponding component of the magnetic field. So by observing magnetization oscillations, you basically can figure out the frequency of this precession, and from it you can figure out your magnetic field. And to observe these oscillations, you apply additional probe pulse, which is usually far off resonance with respect to any atomic transition. And if it's linearly polarized, then due to effect known as Faraday rotation or nonlinear magneto-optical rotation, whenever you have a magnetized atomic vapor, your light polarization rotates with respect to that magnetization. So basically, yeah, you observe polarization of your light. From the polarization, you figure out how your magnetization behaves in time, and from it you figure out your magnetic field. So this technique can be and is done in warm atoms, which makes it compact and portable, as is shown here. The problem here is it only sensitive to a single component of magnetic field. So if you want all three components, you need to use something else. And this is actually the project that I started while I was waiting for my American visa to come here to LA and continue working during my free time. So basically, yes, the idea is that to use the same setup with microwave and optical field that we use for atomic clock. But turns out that if you have an additional magnetic field, then you can not only flip electron spin with respect to its nuclear spin, but you can also tilt them with respect to the magnetic field. And those orientations have different energies, so they correspond to different transitions. So as a result, you observe several optical signal features. The separation between these two features is directly proportional to the magnitude of your magnetic field, so you can immediately know your magnetic field magnitude. And the relative height of these features, just from the experiments, it's apparent that it depends on the orientation of your microwave field with respect to your measured static field. And the problem is that the exact relationship between the height and the angle is not known. Yeah, so that's why I propose to use machine learning technique to basically extract this dependence. But this is still in progress. And the final application is accelerometry and gravimetry, which is the same thing. So if you can measure gravity, you basically can measure any acceleration. So this one is a bit trickier. So yeah, it employs wave properties of atomic ensembles. Yeah, so usually you do magneto-optical trapping and Doppler cooling. So you cool your ensemble, so it starts having like wave-like phenomena. And what you do, you apply 3 pulses. So these 2 contrapropagating laser beams, you basically make a 2-photon transition. And first you do pi/2 pulse, where you put your atomic ensemble into an entangled state. So let's say if it started at the original state called A with a momentum P0, So after this pulse, with 100% with 50% probability, it can be found in the original state, and with another 50% probability, it can be found in the excited state with increased momentum. So the momentum increased by 2 momentums of a photon. Then, well, in this case, they follow different trajectories in space. Then after some time, you apply a pi pulse, where you basically flip the quantum states of atoms on these 2 trajectories. And then you apply another pi or 2 pulse, where you basically mix the states again, and they interfere. And depending on the relative phase between these 2 states, you either have all population in the original state or in some superposition. And it turns out, I don't really understand it, but this phase relationship depends on your gravity or your acceleration. So basically, by observing how many atoms ended up in the excited state or the original state, you can figure out what gravity or what acceleration they experienced. So here in this experiment, they actually measured the gravity from a small cylinder. And nowadays, this has a practical application where some companies actually can measure gravity and using this measurement to figure out underground water deposits or mineral deposits, or even find some catacombs and tunnels. Yeah, so this is it from me. Yeah, now I'd like to answer any questions if you have any. And thank you for your attention.
Awesome. Thank you, Andrei. So what are your questions to Andrei? Scientific or about his career? I enjoyed learning a lot of new stuff. Thank you. So questions from the audience. Come on, Fiat Luxers.
Yeah, actually, I got another question. So in your previous slides, you showed a quantum computing application.
Yep.
I know that you mentioned that it is not your expertise, but I was just wondering, like, what kind of fidelity can this achieve? Because based on the how should I say it? The Rydberg quantum register plot, it looks like a surface code compatible QuBit layout. So I was just wondering, is this already reaching a point where you can actually do quantum error correction on it, something like that, very high fidelity kind of QuBit?
So in general, yes. Yeah, so again, I just recommend you to check out this paper, because it depends on your system, depends on exact layout of your qubits. Yeah, so yeah, just go check out this paper. It's a review of several approaches. Yes, I probably will answer this question. Yeah, but I personally, I don't know. Sorry.
Okay, thanks.
I have a question.
Yep.
Do you think warm atoms and like they could be a viable quantum computing platform that work at, well, without the need for super cryogenics and stuff?
Okay, yeah, so I guess first thing I need to clarify that, yeah, atom-based quantum computing doesn't require cryogenics. So this is all done without additional external cooling. So you need to cool your atoms by means of laser cooling or cooling in magnetic trap, just in order to trap in these optical dipole traps. So in fact, technically, if you have a lot of optical power, you can create very strong optical dipole traps. So you don't even have to cool the atomic ensembles for that. But again, in terms of energy conservation, I guess it's probably easier just to cool them than to waste that much power for trapping. And if we talk about the atomic ensembles, maybe not for the complete quantum computer, but to perform, let's say, one portion, for example, you can do in general quantum memory in a room temperature ensemble. So nowadays it's far inferior compared to cold atoms, but in general you could.
I have a question. So if you look at the other quantum computing platforms, so everyone like is kind of suffering from some problems, like they have challenges in front. For example, ion trapping quantum computers, they are always suffering from noises, and scalability of them are really difficult. So how about atom computing? What are the challenges to have scalable quantum computer based on atoms?
Yeah, so I guess the ultimate problem of quantum computing is that on one hand you want it to be controllable. On the other hand, you want it to be separated from everything else to preserve coherence. So neutral atom-based platforms are good in the sense that they interact weakly with the environment, but as a result, you basically sacrifice the controllability. So external controllability. So I'd say probably that's the main limitation right now. But well, of course, I'm a bit biased, but personally, I believe that for quantum computing, probably because of everything else, neutral-based atom platform is probably the most promising. Again, just because with these optical dipole traps, you can change the physical layout of your qubits even as you go, so even during your computation. But yeah, again, not really my field, so I don't really know all the caveats. Yeah.
So regarding your magnetic sensing, instead of trying to detect how much magnetic field in a certain direction, is it also possible to go backward so that you know the magnetic field component, and then trying to detect what kind of element is inside your sample? Is that?
Yes, that's one of the applications of the magnetic field sensing. Yeah, so you can use it. Yeah, for example, in geological service, so for looking for metal deposits, or yeah, you can use it, for example, in medical applications to by observing magnetic field created by your heart or your brain, you figure out what is happening inside. Yeah, so basically, yeah, in this sense, you're right. Yeah.
Final questions to Andrei. So Andrei, next time we hope your favorite qubits are like things in biology. So let's hope. Let's look forward to next year or something. Okay, thank you very, very much.